So let's talk about rates of change in general. So the basic setup is you have a function and you want to understand how do the values of that function change as you change the input. As you change the input, how do the function values change? How do the outputs change? So let's start with a diagram. Here's our function. Maybe it looks something like this. And I want to know how the values change. So in particular, I'm going to start at a point, let's say x1. And I'm going to look a little bit away from that point, maybe over here at an x2. And I want to know, how did the function change as I went from x1 to x2? So there's a few things that we'd like to give names to in here. One of them is, well, this change in the input, that change in the input, or the increment that we took in x, we're going to denote by delta x. So that's what we've written up here. The triangle symbol is a capital Greek letter delta, and we read it as change in. So that's read, change in x is equal to x2 minus x1. Now as we change the x value, the y values have changed. So there is our change in our corresponding y values. This we're going to denote by delta y. So that's the change in y. And it's just the difference in the function values. So this was x2, f of x2. This was x1, f of x1. And so the change in height is f of x2 minus f of x1. Now the average rate of change is just defined to be, well, it's going to be the slope of the secant line through those 2 points. The average rate of change is the slope of that secant line, or in other words, it's the change in the output divided by the change in the input. It's the change in y divided by the change in x. That's what the average rate of change is. How the outputs changed relative to the change in input. And we have this interpretation that this is the slope of the secant line. Okay, but what we're really going to want to be interested in is not an average rate of change over an interval. In other words, how did the outputs change relative to this big change in input? I want to know, more interestingly, what is the instantaneous rate of change at this point? Right at that point, x1, f of x1. How is the function changing? How are the values changing? Are they changing rapidly? Is the function really steep there? Or are they not changing very rapidly? Is the function sort of leveling off there? That's what I really want to know. What is the instantaneous rate of change there? Well, that is really asking about what direction's the function pointing there. What is the slope of the tangent line? So the instantaneous rate of change with respect to x is the limiting value of the average rates of change. So the average rate of change is delta y over delta x. If we look over smaller and smaller intervals where the x values, the x interval x1 to x2 is really small, taking that change in x to 0, then these average rates of change go towards the instantaneous rate of change, the slope of the tangent line. So the instantaneous rate of change is defined to be that limit, which we recognize as being the derivative at that point x1. So instantaneous rate of change in general is this derivative. We've encountered the derivative again. Tangent line problem, velocity problem, now instantaneous rates of change in general. So let's look at an example. We have a cylindrical tank holding 100,000 gallons of water, and the water is being drained from the bottom of the tank in 1 hour. Then Torricelli's law gives the volume of the water remaining in the tank after t minutes by this formula. So there's the volume at a given time t. If we look at the formula, we see, okay, when t is 0, when time is 0, the volume is 100,000 times 1. So it's 100,000. Great. That's what we expect to start with. When you plug 60 in, you get 1 minus 60 over 60. So 1 minus 1 is 0. So at time 60, the volume is 0. That's what it means by it drains in an hour. So this formula is capturing the way the water is draining. At any given time, we know the volume of the water left in the tank. So we want to find the rate at which the water is flowing out of the tank, in other words, the instantaneous rate of change of v with respect to t as a function of t. What does that mean? The instantaneous rate of change is v with respect to t. That immediately screams to us, we want to know the derivative of v with respect to t. What's the derivative of v with respect to t? So this is asking for the limiting value as delta t goes to 0 of the average rates of change. The change in v over the change in t. At a particular time t, what is the instantaneous rate of change there? We look at starting at that particular time, whatever time it is, starting at that particular time, we go a little bit away from it, sample what the volume is, take away the volume at the time we're interested in, look at the time interval that's elapsed, and look at smaller and smaller time intervals to get the instantaneous rate of change. So it's the limit as delta t goes to 0 of the volume, which is 100,000, times 1 minus t plus delta t over 60 minus 100,000, 1 minus t over 60, oh, and there was a square here and a square here, all of that over delta t. Now we got to go ahead and simplify this, because we already know that if we plug delta t equals 0 in top and bottom, we're going to get 0 over 0, just by the nature of the fact that we're looking at the limit of a difference quotient, the derivative. These are always of type 0 over 0 until you do something with them. So I can factor out 100,000 from both terms. I'm going to factor out the delta t from the bottom too. And what's left is a 1 minus t plus delta t over 60 minus a 1 with a square there, 1 minus t over 60 squared. Now I have to go ahead and simplify this. Now there's a couple of options here. One is to just expand both squares and try to see what cancels. There's another option here, and I'm going to go with the other option, just so you can see what this other option is. I'll leave it to you to do the expanding of both of these squares and do the canceling, but you might not think of the other option, and so that's what I'd like to show you here. What's the other option? Well, it is, notice that this is a difference of squares. I'm going to put the things, so there's something squared minus something else squared. It's a difference of squares. We know that a difference of squares factors. What does it factor? It factors into the difference of the two things multiplied by the sum of the two things. Right, so I'm imagining we're staring at something like a squared minus b squared, and that is equal to a minus b times a plus b. What is a? I'm imagining this whole thing is a. What is b? I'm imagining that whole thing is b. And so this becomes then 1 minus t plus delta t all over 60 minus 1 minus t over 60. And here it's 1 minus t plus delta t all over 60 and a 1 minus t over 60. So let's go see what each of these pieces does. I'm going to do this in a different color. They're sort of side calculations that are done on the side. We have 1 minus 1, that's 0. We have a negative t over 60 plus a t over 60, that's 0. We have a negative delta t over 60. And this piece, I have a 1 plus a 1, so that's a 2. Negative t over 60, another negative t over 60, so that's negative 2t over 60. And a minus delta t over 60. So this becomes the limit as delta t goes to 0 of 100,000 over delta t. negative delta t over 60 times 2 minus 2t over 60 minus delta t over 60. And so notice that we get some cancellation of these delta t's. So this becomes the limit as delta t goes to 0 of 100,000. And there's a negative, so I'll bring that out front. There's a 60, put that downstairs. There's a 2 minus 2t over 60 minus a delta t over 60. And now as delta t goes to 0, the only place delta t appears is in that last term, so it goes to 0. So this is negative 100,000 all over 60 times 2 minus 2t over 60. I can factor out a 2 from each piece. That'll cancel with one of them in the 60 below. And so I get negative 100,000 over 30, 1 minus t over 60. And there is our derivative of the volume. That's the instantaneous rate of change of the volume at a given time. What are the units? Let's leave a little bit of room over here. What are the units for this? Well, the way we get the units for this rate of change is to go back and see how is it defined. How is the rate of change defined? V prime of t is the limiting value of delta v over delta t. So right here, we know immediately what the units are. It's the units in v divided by the units in t, because that's what the units of the numerator are. They're the units of v, and the units of t are the ones in the denominator. And the rate of change in the volume is just the ratio of these things. And you take the limit, but it's just the ratio of these things. Volume is gallons. Time is it minutes or seconds? We have to look. Okay, it's minutes. So this is gallons per minute. There's our units. As a reality check, let's see if this makes sense. So here is our graph. This is going to be our t-axis. This is going to be our v prime. That's our derivative. Let's see what this is. Well, what's going on at 0? When we plug t equals 0 in, t equals 0, I get a value of, so v prime of 0 is negative 100,000 over 30. So it's down here. Negative 100,000 over 30. When time is 60 at the end of the hour, plug 60 in, you get 1 minus 60 over 60, so that's 0. So the rate of change is 0. And it's a linear function, so it connects these two. So maybe I'll do that in blue. What does this represent? Well, it's the rate of change over time. At time 0, the rate of change in the volume is negative 100,000 over 30. It's negative because volume is decreasing. The water's draining from the tank, so the volume is dropping. So it's dropping quite rapidly. And then, as time goes on, the instantaneous rate of change in the volume becomes closer and closer to 0. So it's tapering off. Not as much fluid is flowing out at any given moment. Until the very end, at time 60, the rate of change in the volume is 0. Nothing's flowing out anymore. The volume's not changing. So rapid flow at the beginning out and slowly dwindling until right at the very end, the fluid is not flowing out anymore because the tank is empty. This last example comes to us from business and economics. So suppose we have that the quantity in pounds of gourmet coffee that is sold by a coffee company at a price, p dollars per pound, is given by this function. The quantity is some function of p, or price. So here, p is price, q is quantity. The quantity sold. What do we know about these? Well, we know they're units. Price is in dollars. What is quantity? That's in pounds. And we have this functional relationship that as price changes, this is how the quantity is changing. What is meant by the derivative of f prime of 8? What is meant by f prime of 8? and what are its units? Well, f prime of 8, that's the derivative of the quantity function when the price is 8. What does this mean? This is the rate of change in the quantity sold when the price is exactly $8. Okay, so that's precisely what f prime of 8 means. Now, it would be nice to have at least a visual interpretation of what this is. Again, it's the slope of the tangent line, but what's this really saying? What is f prime of 8 really saying? In other words, can we get some sort of qualitative idea of what it is? So here is, let's say, our function. That's our quantity versus our price. And we're interested in particular, what's going on when the price is $8? Well, there is how much quantity is sold. That's f of 8. What is f prime of 8? Well, geometrically, that's the slope of the tangent line to this curve. So it looks something like this. And so here, our slope is f prime of 8. What does that actually mean? Well, the tangent line is supposed to be a good approximation to the function near the point 8. This tells me that as I move a little bit away from 8, as I increase my price a little bit, the tangent line, the steepness of it, is telling me how much my quantity is dropping, the rate of change in my quantity. How much less coffee am I going to sell if I increase the price? So, for example, to get a big picture of idea what's going on here, suppose I increase my price by $1, from $8 to $9. This is the actual quantity sold when the price is $9. So when P equals $9. What is the tangent line telling me? Well, the tangent line is giving me here, it's giving me an approximation. If the tangent line is a good approximation to the function near 8, then the points on the tangent line near 8 should be close to the points on the curve. So here, this is the approximation, or approximate quantity sold when price equals $8. So when price is $8, that's an approximation. Could I figure out how much this dropped then? F of 8 is the original quantity sold. How much did it drop to get that approximate value? Well, we've got a little right triangle here. The base is 1, because I went from $8 to $9. What's the slope of this tangent line? That's f prime of 8. Ah, the slope is f prime of 8. The slope should be rise over run. So that means this is f prime of 8, this height here. In other words, f prime of 8 is approximately how much your quantity sold has dropped when you increase your price by 1 unit. So this is the actual meaning of f prime of 8, and this is how we interpret it. It tells us how much, the rate of change, the instantaneous rate of change at that point, tells us how the function's changing. For every unit increase, the derivative is telling us roughly how much the function has changed by. Okay, so this next question, is f prime positive or negative? Explain. Well, okay, I sort of already answered the question above by the way I drew the diagram. I drew the tangent line here with a negative slope. Does that seem reasonable, though? Probably should have asked this question before I drew the tangent line. Does it seem reasonable that f prime of 8 is negative? Well, f prime of 8 is supposed to be how does the quantity change when you increase the price? If I increase the price, starting at $8, if I increase the price to $9, I expect to sell less coffee. Expect the quantity that I sell to drop. After all, you're probably going to lose customers. You're not going to gain any customers by increasing the price probably, so you expect to lose customers. So you expect to sell less quantity. So we expect it to be negative. Increasing the price should reduce the quantity sold. So we expect it to be negative. All right, that's it for this section. Thanks very much for watching, and we'll see you again next time.